Maximizing photovoltaic system performance, insights on partial shading and power electronics. Harnessing the power of the sun, PV systems are transforming the way we generate electricity. However, while the sun's energy is abundant, harnessing it effectively in all conditions remains a challenge. One of the significant hurdles that PV systems face is the issue of partial shading. Max performance under partial shading. PV generators mounted on rooftops often encounter varying degrees of shade. The complexity of this challenge lies not in the presence of shade itself, but in understanding how to navigate it. Surprisingly, the solution isn't necessarily about introducing more sophisticated power electronics to the system. The effectiveness of power electronics hinges on various factors, such as the degree of shading, the number of PV modules in a single string, and the overall size of the installation. As owners and PV planners seek answers to this intricate problem, they can find insights from conference presentations and the upcoming technical report from IEA PVPS Task 13, available on the IEA PVPS website. These resources shed light on a topic that has puzzled experts for decades: the evolution of PV technology. Over half a century ago, the introduction of bypass diodes in PV modules was a game changer. These diodes acted as conduits to redirect current flow in cases of partial shading with remarkable efficiency. Yet, the journey of PV technology has been marked by constant evolution. New DC/DC converters have taken the reins, offering the potential to operate each PV module at higher voltage values with lower module currents. This innovation outshines the simple serial connection of all modules to power the conventional string DC/AC inverter. However, it's essential to note that this isn't a one-size-fits-all solution. The situation where DC/DC optimizers shine is relatively rare, typically occurring when a single solar cell in the module is shaded by no more than 40%, and 3 bypass diodes are used. While the theoretical potential for energy gain with DC/DC optimizers is promising, it must contend with real-world losses, which typically account for about 2% of the annual yield, significantly higher than traditional PV module serial connectors. Challenges in PV planning. One of the challenges in the world of PV planning is the reliance on typical commercial PV planning tools that tend to overestimate the capabilities of DC/DC components. These tools often rely on the above datasheet values as an average for all optimizers within the system. However, they may not adequately consider the complex shading situations of each cell in the module, the role of all bypass diodes, or the orientation of the module on the roof. These tools used by PV planners typically estimate the average module power output relative to the percentage of the shaded module area. While this provides a basic overview, it doesn't account for the intricacies of partial shading scenarios. The result is often an inaccurate reflection of real-world performance. Popular findings. The complexity of addressing partial shading has led to in-depth research and findings that offer valuable insights. The Zurich University of Applied Sciences, the German, Sursche Hochschule für Angewandte Wissenschaften, annual simulation results, based on shading analyses of each individual solar cell, paint a clear picture. These models are built on the losses of commercial DC/DC optimizers measured indoors at relevant operating points. The losses observed are approximately 2% lower than the manufacturer's datasheet information, a significant variance that has been documented in various conferences, papers, and magazines. Optimizing PV plant design. The design of an optimum PV plant hinges on the selection of one of the 3 PV power electronic systems. Whether to opt for standard PV modules or shading-tolerant PV modules is a decision with long-term implications. In the years to come, a wider range of the latest PV module products, along with new low-voltage PV inverters and multiple maximum power point tracking (MPPT) inputs, will become available. These developments aim to facilitate the creation of long-term, robust systems that are both efficient and environmentally friendly. Cost considerations and future insights. PV inverters typically require replacement once during the 25 years of PV plant operation. However, the scenario becomes more complex when it comes to DC/DC optimizers. Operating at significantly higher temperatures on the roof, these electronics may face more frequent replacement needs. In Switzerland, a country with a robust market for single-family houses, it's common to budget for replacement costs ranging from about 1,000 to 3,000 Swiss francs. These costs often include fall protection measures, further underlining the financial aspect of optimizing PV systems. The need for informed decision-making. In a fair market, end customers must gain a clear understanding of the various options available for their PV rooftop system. Choices range from string inverters and independent optimizers to all optimizers and the use of individual shading tolerant modules. It's not just about assessing potential electrical performance gains, it's also crucial to consider the associated risks of possible replacement costs. With these factors in mind, customers can make informed decisions that align with their long-term goals and budgetary constraints. Collaborative efforts for improved PV planning. The exchange of factual information among different stakeholders in the PV industry is a catalyst for progress. The development of improved commercial PV planning tools and an enhanced experience for PV system planners are the results of this collaboration. IEA PVPS Task 13 is at the forefront of these efforts, with plans to publish a final report in 2024. This report will include recommendations from international experts, coordinated by the aiming to guide the industry toward more effective and efficient PV system planning. The report will be available at Reliability and Performance of Photovoltaic Systems, IEA PVPS.